ionization, which I will, of course, show you how to do when we get to finding this value out right here. Okay? So, again, do our little mini ice thing here. Minus x here, x here, x here. So this is x times x, which of course equals x squared. And this is going to be 0.05 minus x. So we're going to make a quadratic equation out of this, and then we're going to be setting this up for quad form. So yes, if you don't have quad form, you got to get it. And if anybody has their cord with them, and I will transfer it over for them. If you don't have your cord, I think I've got a couple extra cords I can use for that. We'll see. I'm not sure. They keep coming and going. I don't know why. So let's do the H positive thing here first. So we know that 2.25 here is going to equal to x squared over 0.05 minus x. Multiply both sides by 0.05 minus x. That cancels out, leaves x squared. And when I multiply this out, I get 1.1 times 10 to the negative 6th minus 2.2 times 10 to the negative 5th. X equals x squared. Bring the x squared over here. Rearrange everything in order from x squared down to no x's. So negative x squared. Negative x squared minus 2.2 times 10 to the negative 5th x plus 1.1 times 10 to the negative 6 equals 0. That gives me my quadratic. Go to quad form. Negative 1 is my A. Negative 2.2 times 10 to the negative 5th is my B. And 1.1 times 10 to the negative 6 is your C. Big C, little c. Big C, little c. Alright, so quad form that thing, and you're going to get two answers. A negative answer and a positive answer. Quick tip. There's no such thing as a negative concentration, so you ignore the negative answer. The positive answer you get out of this is x, which we've already established as a positive. And according to what I have here, that is equal to 1.04 times 10 to the negative 3 moles per liter. Please use scientific notation. Don't give me those goofy zero things and then you don't space properly. I really don't like that. So just type it out in scientific notation. Alright, percent ionization. What that means is what percent of the original concentration of reactant you had actually broke down, percentage-wise. So this is what we ended up with, divided by, this is what we started with, 0.05. That's molar, they cancel out, times 100. And that'll be your percentage, which turns out to be something like 2.08%. So about 2% of stuff breaks down. That's kind of high for a weak acid. So, whatever. 33. For this one, they give you the pH again. pH is 2.68. And they give us, they tell us that this is acetic acid. So we have to go to the chart, page 727. So make sure you're using that chart for your weak acids. When they say, oh, here's a weak acid, good luck. You need to find it on that chart. And that is equal to 1.7 times 10 to the negative 5th. And what they don't give you is the original concentration of the material. So we want to know what is the original concentration of the acetic acid, which I'll call, of course, HA. Ha! Original. Alright, so, again, HA aqueous, which works really well because acetic acid gives a name. Aren't I the clever boy? H positive aqueous plus A negative aqueous. Okay? Okay. So, Ka for this is 1.7 times 10 to the negative fifth. And then X, and then concentration minus X. This is going to give us, well, if the pH is 2.68, then I can find the H positive concentration, which is our X, and that's going to be 10 to the negative 2.68 power. So you hit 10 carat negative 2.68 your calculators, and you get 2 points, you get 43. You get, oh, there's 2.09. That doesn't sound right. Okay, well, I guess I'll go with it. 2.68. It's 2.09 times 10 to the negative third, I guess. Alright. Moles per liter. So that's my X, so I'm going to plug that in for X here, and there. So X times X is X squared. So this is 2.09 times 10 to the negative third squared over some concentration, which I'll call Y now. Let's call it Y. Why not? Minus 2.09 times 10 to the negative third, since it's minus X. Clever that way. So, I'm going to multiply this side over here by Y minus 2.09 times 10 to the negative third. And that's going to eliminate that over there. Okay. So, this is going to give me 1.7 times 10 to the negative 5. Why not? And the negative 2.09 times 10 to the negative 3 times that gives me 4.3, no it doesn't, 3.55 times 10 to the negative 8 equals, and then I'm going to get 2.09 squared, and then negative 3 squared, which is going to give me 4.37 times 10 to the negative 6. Okay, so now I'm going to, again, this is algebra. I got y here, got a subtraction, got a multiplication. Since I'm going backwards, I'm going to have to add my 3.55 times 10 to the negative 8 to both sides, which is like a 4 times 10 to the negative 6. So that cancels out. That leaves me 1.75 times 10 to the negative 5y equals 4.41 times 10 to the negative 6. Now I have to divide by 1.75 times 10 to the negative fifth. Why does that sound like it's not working out right? 4.41. Times 10 to the negative 6. Oh, yeah, that's right. Never mind. And y then becomes points. And what is the point here? 259 moles per liter. So the original concentration of acetic acid is 0.259. Okay? Last problem. Then I'll let you have some real fun. Play with your calculators and stuff. This one we're dealing with hydrofluoric acid. Hydrofluoric acid has a Ka, according to page 727, of 6.8 times 10 to the negative 4. And we are given that the concentration of HF is 0.04 molar. And the question here is, what is the pH? Which means, of course, that I'm going to have to find concentration of hydrogen in order to figure out the pH. So those go together. I need to know both these things. First this and then that. Well, this is actually a kind of an easier problem. The other two we just did. So let's just go ahead and go right to, well, I'll use HF. So let's just stick with HF. So HF, aqueous, double arrow, H positive aqueous, plus F negative aqueous. Okay, so Ka is concentration of H positive times concentration of F negative over the concentration of HF, and that equals 6.8 times 10 to the negative 4. And do my quick little ice thing here. We got 0.04 of this, and we're going to lose x here, we're going to gain x here, we're going to gain x here, which means that's going to be x squared on top over 6.8 times 10 to the negative 4 minus x equals, how about not that number, because that was really dumb, that was the Ka, I should not have done that. It's 0.04 minus x equals 6.8 times 10 to the negative 4th. So I'll multiply 0.04 by both of those, I get x squared left here, that cancels out. And I get that equal to 2.72 times 10 to the negative 5th minus 6.8 times 10 to the negative 4th x. Now I'm going to move stuff around. I'm going to move this over here and then rearrange the order of my terms there to get a quadratic. So 0 equals negative x squared minus 6.8 times 10 to the negative 4x plus 2.72 times 10 to the negative 5th. So that means negative 1 is my A, negative 6.8, E, negative 4 is my B, and 2.72 E, negative 5 is my C. See what I mean? And plug all that into quad form, punch it out, you get an answer for X, which is our hydrogen ion concentration, coincidentally enough. 5.13 times 10 to the negative 3rd moles per liter. Then to find the pH, to the negative log of that thing right there, and I get 2.28. And that, ladies and germs, is how we do quad form for Kas and weak acids. Have fun.